We know that in the Newtonian world, when I drop this orange, it will accelerate downwards at 9.8 meters per second squared, or g. In fact, Newtonian mechanics works well for describing many physical phenomena, like the motion of this ball. Problems arise when we look at other systems, like this deceptively simple-looking large-angle pendulum. It's attached to a spring, allowing 3 dimensions of oscillation. Attempting to calculate the forces in the bob in the vertical, horizontal, and angular directions is sure to result in a second-order differential equation nightmare. That's where a new branch of physics comes in, Lagrangian mechanics. What makes many problems so difficult in the Newtonian world is that Newtonian mechanics deals with forces, which are vectors. Lagrangian mechanics deals with energies, which are scalars, and much easier to add. Lagrangian mechanics was first introduced by French mathematician Joseph Louis Lagrange in 1788 as a mathematical reformulation of Newtonian mechanics. And while it doesn't introduce any new physics concepts, it treats constraints in the generalized coordinate system, making the most difficult problems in Newtonian terms solvable with a function called the Lagrangian. The Lagrangian is equal to the difference between the kinetic energy, T, and potential energy, V, of a system, and is a function of generalized coordinates. What do I mean by generalized coordinates? In its most basic form, consider this simple pendulum. As the bob swings, you could see it follows this circular path. Now we could think of this as moving in the x and y directions, but that's a lot harder than confining it to one dimension of motion, the angle it forms, since the string length is constant. All we need now is the Euler-Lagrange equation. Don't be frightened, it looks scary, but think of it as a fancy version of Newton's second law. And while each employs its own mathematics, both systems predict the same physical outcomes. Here's proof in one dimension. We'll call the ball's vertical position coordinate y. As it falls, it has kinetic energy T equal to 1/2 my dot squared. Y dot is simply the first time derivative of position, or velocity. It also has potential energy V equal to mgy, giving us our Lagrangian. Recall the Euler-Lagrange equation. That cursive d is just simply partial derivative, meaning that we treat one variable, ignoring the rest as constants. Partially differentiating our Lagrangian with respect to y and y dot gives us this. Taking the time derivative of the right side leaves us with this, giving us the second derivative of position, which is acceleration. And there you have it, the Lagrangian version of solving for g. Aside from being a powerful mathematical tool and being of use when Newtonian mechanics is inconvenient, the Lagrangian has many applications in quantum mechanics too.